Hello students, now we have already started with rotational motion, and one of the foremost term what you are going to come across in this chapter is moment of inertia. Now why is it required? Was our knowledge of energies and laws of motion, weren't those enough to solve a question when a body is rotating and going? So the answer is yes, those were enough, but this term brings a bit of convenience in solving. So I would say this term is a term of convenience for us, and you will soon see how. So let me just demonstrate while we are solving for, say, kinetic energy. Mind you, the three pillars of solving for any mechanics question had been F is equal to ma. The force gave you the relation of the acceleration provided the mass was known, and your force itself was the rate of change of momentum. So this and this is the same thing. So the force was rate of change of momentum, and then what was your momentum? Your mass times velocity gave you the momentum. It was a vector in the direction of the velocity. Force is also a vector in the direction of the acceleration, and you had your kinetic energy as half mv square. Yeah, these were enough to solve any question, and I'm going to use these to solve a question. But later on, what we have learned is about center of mass, whereas we assume that whole of the body is situated at a single point, which is called the center of mass of the body, and the velocity possessed by the whole of the body is the velocity possessed by the center of mass, which is called the velocity of the center of mass, VCM. If we are going into the world of rotation, we might get into a problem if we ignore the fact that the whole body is actually a distributed body and is not, everything is not lying at the center of mass. So you have to use your discretion to use when to use the center of mass and when not to use the center of mass. So I'll just demonstrate how we have to be very careful when we are handling rotational motion, body which are rotating. So let me just make a body which is not rotating in fact, and say these masses, these three masses, all having same mass m, connected by a very light rod, massless rod, so it makes a single body of in fact mass 3m. So these three are connected and makes a mass, and that is going forward with, say, v velocity. Now if I ask you what is the kinetic energy of this body, so the kinetic energy would be the kinetic energy of this mass plus the kinetic energy of that mass plus the kinetic energy of that mass. The kinetic energy the kinetic energy of the whole body is the kinetic energy of the individual masses. So that gives me half mv square plus half mv square for the other one, and another half mv square for the third one. All three are going with the same velocity v forward. Right now, somebody would have said that why to do it in this long process? This can be considered as a single mass of 3m. So that's, and the mass is lying at the center of mass, and I should have not drawn a big circle to depict it. It is actually a point mass. So of having a mass of 3m, and the point is having a forward velocity of v, because that central point will have a forward velocity of v. The center of mass is going with vcm, which is v forward, and the mass itself is 3m. In that case, what would have been the kinetic energy? Half 3m v square. Now what is the difference between this answer and this answer? Here I have been very careful in writing the energy of each masses, and here I have used the concept of center of mass and just written it in one go. This looks very convenient to write, and this isn't, and both are giving you the same answers. Now the thing is, if they are giving the same answer, we might feel that this is the right way of writing it, but this isn't. What I'm going to show you is, suppose the body was not translating like this, it was rotating also. So till now what we have done is bodies which are going forward and not toppling or rotating, it's just going forward. The whole thing is going forward with a certain velocity. So what is happening is each and every particle of the body is having the same velocity. Now if I do the kinetic energy of each and every particle of the body, which will be half dm, and all of them are having v square, and integrate that will be the total kinetic energy, which will give me nothing but half an integration of dm, and v also outside the integration square. So this integration of dm, all the dm's added is going to give you the total mass. So becomes half mv square, where m was the total mass of the body. So it looks futile in doing this, and we wrongly assume that what we have done is we have taken the center of mass of the body to be here, and we have done the velocity of that. So this mass is the total mass which is concentrated at center of mass, and the velocity of that, which, thinking it that way might be a little misleading. Thinking it this way is absolutely all right. That's the basic concept. So this is absolutely all right, provided we are careful. I'll just demonstrate what do I mean by being careful. Suppose this body was going round also, rotating with omega. And before I do that, before I do this question, going forward and rotating, let me just ask you one thing. And I hope I'll put it in red so that you understand that how wrong it is. Say this body is having no forward velocity and it is going round with omega. So what do you think? What do you think is the kinetic energy of the body? Is it zero? No, obviously it is not. The top mass is having some velocity. Say this distance is say d. This distance again is d. I'm just keeping same variables m, so that the calculations whatever we are writing are absolutely simple. So the velocity of the topmost part is omega times d, the velocity of the bottommost part is backwards omega times d, and the velocity of this is 0. Now in my careful approach, if I ask you what's the kinetic energy, then in my careful approach what I'll get, in blue I'll get the right thing, which is half m velocity of that thing square wd whole square plus half m velocity of the center guy square. So that is half m0 square, and then half m the bottom one, whether it is going forward or back, it is a scalar quantity, omega d square gets added. So what we have, it's a non-zero quantity, half m omega square d square, twice of that. So it's a non-zero quantity. Had we done this superficial approach, I would say that I'm considering the whole thing to be at the center. So if the whole thing was at the center, 3m, what was the velocity? vcm is obviously 0. Part is going forward, part is going back, say of same masses, and the center part is having no velocity. You can do your m1 v1 plus m2 v2 plus m3 v3 divided by m, and you'll get the velocity as 0. So that's the average velocity, in fact. So that is 0. So if I use this, then my kinetic energy would be, in red, kinetic energy would be half 3m is the mass, 0 square, which is absolutely wrong. This is the correct answer. So you see, when the body has started rotating, then your answer is different when you have a careful approach. In fact, I'll emphasize that the answer is more than what comes if you consider the whole body to be at the center of mass. It is always more. We'll come to that. May not be in this session, but please remember it, that your kinetic energy is going to be more than what you will get if you consider the whole body to be at the center of mass alone. Now, if the body was rotating and going forward, then what happens? Apart from having a v velocity forward because of the body going forward, it will have an extra omega d velocity, omega d extra added to that v. So it's like this, like if it was not going forward and rotating, the top point had a velocity of omega d, but it is going forward and rotating also. Had it been going forward and not rotating, the velocity would have been v. So it goes forward in a second, say v forward, and then it has rotated also, so it has further gone wd forward. So the total amount gone forward is wd plus v. So, and similarly, the bottom part, it has gone backwards with wd, but the whole body has gone forward with v. So it has gone forward with v minus wd. It could have gone backwards with wd minus v, whichever way you want to write it. So this would be a small velocity. This is, so I'll make a smaller arrow over here. If at all forward, it could have been backwards also, depending on how much is omega and how much is v, and that's a bigger velocity. Now what is the velocity of the center of mass? The velocity of the center of mass is again v. It is v plus something, v and v minus something, same masses. So if you do a m1 v1, m times this much plus m times this much plus m times that much divided by 3m, you'll get v again. That's the velocity of center of mass. So if I do this approach of 3mv square, I'll get this as the answer. This as the answer, and I hope you have understood that if I do the careful approach, I am going to get another answer which is not going to be that, and I have emphasized that I am going to get an answer which is more than this. Let me see, do I get that or not? Half for the top body, m v plus omega d whole square, then half m for the central body, v square plus half m v minus omega d the whole square. So you see we get a v square from here, we get a v square from there, we get a v square from there. So we do get a m and a 3v squares, so which is equivalent to that, which is that. So it takes care of this much part, but we get extra stuff. We get extra stuff. We have this minus v omega d plus v omega d and minus v omega d cancelled out from here and there, but we still have your omega square d square and omega square d square getting added. So a half m omega square d square from both places are getting added. So from both places. So this is an extra term. That's the real kinetic energy. If I have to contest that whether this is right or that is right, then obviously I've been more careful over here. This is right. That is, I've assumed things which that assumption was not actually correct. So a bit on why we always get more than what we get when we do a simplistic approach and not the careful approach. So why we get that extra term always? Because in any given body which is rotating and the center of mass is going with, say, a certain velocity, I'll take a number in fact over here for convenience, 10, then some would be going with more than that and some would be going with less than that. Then only that 10 was the weighted average. So, and in fact, if I have taken equal masses and also, then those are going with say 11, then these would be going with 9, then only the average will come 10. So even with masses, you can do m1 v1, so the literally weighted one. So that way also you can check. So what I'm trying to go on to is to show you a mathematical certainty that if I do a kinetic energy calculation, which is a 11 square plus 10 square plus 9 square is not same as your 3 times 10 square. Not at all. Why? Because 11 square is more departed from 10 square than 9 square is. You go one up, but the square makes you go more away than 10 square, than the 9 square makes it go away from your 10 square. Like over here, 10 square is 100, 11 square is 121, so it is 21 away. Now is this 9 square 21 less than 100? No, it is not. It is only 19 less than 100. It is 81. So if I add up all three, this adding up is not going to give me 3 times 100. It is not going to give me 300 because it has been 21 more and only 19 less. So it will give me 2 extra. So what will I get is, on adding this, instead of getting 300, I'll get 302. So it's a mathematical certainty that if some things are less and some things are more, and if you square and add, then the result will not be that's the simple average result. So anyways, I think I've made the point clear that when the bodies are rotating, you can't handle it in a very simple way like the whole mass was at the center of mass and do the stuff with the center of mass. So this formula is applicable provided you take each and every mass carefully. So that becomes quite a job. That becomes quite difficult. In fact, akin to this formula would be, I hope it is in the frame, torque is equal to I alpha. Your momentum, instead of momentum, we'll have angular momentum, which is R cross your linear momentum, and kinetic energy will have an improved formula. So these formulae, your angular momentum, why do we introduce an angular momentum thing? Because it is going to, a rate of change of angular momentum is going to give me torque, and the torque is going to give me alpha. And while doing those, we have to literally see what is happening to each and every particle. Now that seeing, it sounds tough, it is tough, if in fact if it is any random body given to you. So to make our life easy, that seeing each and every particle is what we do in moment of inertia. So I'll just rub the board and go on to that, like what, why, wherein the moment of inertia term is coming in and how it is helping you. And yes, don't worry about the angular momentum term and the torque term, everything is going to be explained in time to come. Let us concentrate on this moment of inertia. Nice name depicting what it stands for, so we'll come to that. Let me take up a situation where, say, you have point of rotation and you have a rod. Instead of taking a continuous mass, let me again take a rod which is connected by a light rod, and it has got many beads at random separation, may not be same separation, many of them. So the mass of the rod is mass of all these beads added, because this thin line is just a rigid connection between them, and the whole thing is rotating about this axis. This axis is going outside, inside the board, from out to in or in to out, whatever. This is the axis, and it is rotating with omega. Let the masses be, say, m1, m2, m3 and so forth, m4, m5, mn, and this is x1. So that distance from the point of rotation, from the axis of rotation in fact, of mass m1 is, say, x1, and the next one is, say, x2, next one is x3 and so forth. Okay, now if I ask you what is the kinetic energy of the thing which is going round, then what will you do? You'll do the careful approach, right? Like suppose you have a fan, a ceiling fan, and it's rotating. The center of mass is going nowhere. Do you say that the kinetic energy is zero? The blades are vigorously rotating, and it can do a good harm to somebody in the way. It is having a lot of energy in it, and we can't simply say that a center of mass is having zero velocity, hence the total kinetic energy is zero. That's absolutely wrong. So we'll actually be doing the kinetic energy of each and every particle as carefully as we can. So that becomes quite a job. So this is a similar situation. This rod is rotating like this around this point, and we have to get the kinetic energy. So we'll do a careful job. So what is that careful job? Instead of finding the center of mass, that's again quite a job, and then finding the velocity of that center of mass and doing a half mv square, we'll not do that, because now we know that doing that results in an answer which is less than the actual answer. So what's the actual answer? The actual answer is, we'll take each particle and do a half mv square for each. So half m1, what is the velocity of that? Velocity of that would be omega times x1, right? All of them are going with omega. The whole rod goes, the angle swept per unit time is same. So after a while it is here, but the angle swept by all the masses, that mass has come here, that mass has come here, angle swept per unit time is same. So but the distance covered is different, so they have different velocities but same omega. So that's a rigid body for you. So what's the next mass? m2, and the velocity omega, same omega times x2 square, and the next mass half m3 omega times x3 square, and dot 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 so forth. So what we see over here is half is common, omega is common to all of them. So shall we write omega square outside, and what we have is m1 x1 square plus m2 x2 square plus m3 x3 square dot 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 dot. Now this term is independent of how much was the omega, and this big fat term is coming when you calculate the kinetic energy. So this big fat term for this body is the moment of inertia of the body. So this term is the moment of inertia. Ke is written as moment of inertia of the body about this axis. Now what is the emphasis over here? This moment of inertia is not of the body in all situations. It is of the body about this axis. Had the axis been here, then the distances x1, x2, x3 would have been different, and this term would have been different, and this would have been different. So unfortunately, when we know a body but we don't know the axis, then we don't have the moment of inertia. If the axis changes, the moment of inertia changes. In fact, if I have a situation where this pen is rotating about this, okay, let me hold it up. This black pen is rotating about the blue axis. It is like this, and later on the blue axis shifts over here and rotates like this. I have done a painful integration to find out the moment of inertia. Why integration? Because the masses are distributed all along, and I have done an integration to find the moment of inertia. And later on they say that no, the axis is here. Then again I'll say, oh my god, we'll have to do an integration again. So thankfully we have a system of we have a trick which we call as parallel axis theorem. We have some theorems that's nothing but a maths trick where once we have got the moment of inertia across any given axis, we can find the moment of inertia about any other axis without doing the calculation. So anyways, that was off topic. Let me come back to this. We are going to come to that later. Let me come back to this and emphasize the point over here again, that moment of inertia is taking care of not only all the masses. Kinetic energy simply for a center of mass, if we had considered, was taking care of only the mass. It is taking care of not only all the masses but also how they are distributed. Had all the mass been at the end and it was rotating with omega, it would have, all the masses would have got tremendous velocity and the moment of inertia would have been big. This omega would have been same, but this term moment of inertia would have been a large term, because m1, x1 would have been a big value, x2 would have been a big value. Similarly, if the things were nearer to the axis, the moment of inertia would have been less. So moment of inertia depends not only on the mass but also the distribution of the mass. Now this kind of term, when we are going to calculate anything like angular momentum, you are not very familiar with what is angular momentum. I'll give you a small briefing and try to calculate angular momentum of this body, and then later on torque. If you are going to do anything, this term is going to crop up. Now since this term is going to crop up again and again and again, so what we do is, if we have to do stuff with this body, we pre-calculate the term and keep it for ourselves. So like that, we have a lot of different kind of bodies and we'll have to do a lot of different calculations. But thankfully what comes in exam is a specific list of bodies, and for those bodies we have done moment of inertia calculation. We have prepared ourselves to deal with rotation questions for those bodies by doing a homework, because that term is going to come again and again no matter what. You might say that if you have a rod, the axis of rotation has changed, then the moment of inertia has changed, then as I told you, there's a trick to do that. So a pre-calculation through one of the axes gives a good idea of what will be the moment of inertia, gives a mathematical certain formula for what will be the moment of inertia of a shifted axis. So, and parallelly shifted axis, so we can't get in all cases. Okay, we have two specific cases when we can get, but not in all cases. So the thing is, since the list of bodies are limited, we have done calculation for that. So this is the list of bodies, and what you'll see is with the mass and the dimension of the body, they have also given what is the axis of rotation of that body. So moment of inertia has been calculated through which axis is specific. So moment of inertia is not of the body alone, of the body around a specific axis. Okay, so if you say that 1 by 12 ml square is the moment of inertia of a rod, then that's not a complete sentence. You'll have to say that it is of a rod about its center of mass, about an axis, about a perpendicular axis, in fact, going through its center of mass. And you have to define the axis. If the axis is inclined, again the moment of inertia is wrong. So you have to have a defined axis, and then only you can get the moment of inertia. Now, is this term moment of inertia so important that we pre-calculate for all the bodies? Yes, it is, because I'll just show you that when we calculate the angular momentum, again the term is going to come up. So we no matter what we do in rotation, that term will come up. Ultimately, if you have to calculate, if I put a force on this and I don't know stuff like moment of inertia and all, I've used my basic knowledge of laws of motion and try to find out what is the acceleration of all these things. They are connected, it's a rigid body. So what will happen is all have different accelerations, but they will have the same alpha. So if you have to find out the alpha, again if I am trying to do from the basics, seeing the tension, how the force is transmitted from here to there, and I am trying to do from the basics, then again what I'll see is this term moment of inertia comes up. It will be quite a job. Okay, by mistake I rubbed off the whole board, so the situation is same. There is a body with several masses on it, m1, m2, m3, at a distance of x1, x2, x3, and this is rotating about a certain axis here. Now we want to calculate the angular momentum. So this part of the lecture is not to tell you what is angular momentum. This is to emphasize that even when we are calculating angular momentum or any other stuff with the rotating body, again the term which is your moment of inertia is going to come up. So just to emphasize that, but before we do that, I will tell you the basic formula of angular momentum and what it means with a point body. Say you have a point mass m going with a velocity v forward, and I ask you what's the momentum. M into v is the momentum. Yeah, that's the momentum of the body. What's the angular momentum of the body? If I ask you what's the angular momentum of the body, then you'll say about which point. Say about which point, then about this point is what I'm asking, about this point O. So what's the angular momentum? So you need to know the distance. So say this distance is r, velocity is v, angular momentum is given by the formula mr cross v. So in fact it will be m r perpendicular times v, or m r v perpendicular. Now what do I mean by that? We are doing a simple cross product. So before we do that cross product, we need to know this r is from O to the mass or mass to O. So the thing is, in an angular momentum, it has been defined like this. Okay, it has been defined. Why it has been defined? How does it help me? So ultimately the goal was to get your torque and other things very simply by differentiating this angular momentum by seeing the rate of change of angular momentum. So for now we'll just confine our thing that it has been defined. So we'll not go into the term why and how, and even the physical significance will not speak about it right now, a bit later. So the defined thing is the radius is from the point of rotation, or from the point where you think, from where you are studying the body as a thing which is rotating. So in fact the body is going forward, it covers some angle, so it has got some rotation. So had it been going like this, then with respect to this point it would have covered no angle, it would have no rotation, it will have no angular momentum. So angular momentum is if the body is sweeping some angle, and it has been defined like this. R is from O to M, so R vector is this way. So I'll just make it in black pen or say blue pen over there. R vector is that way, R vector. So if the angle between R vector and V vector is theta, then what we get from here is M R V sine theta. Now what is this R perpendicular and V perpendicular? So what we could have done is we could have broken our V in two parts, along the R and perpendicular to the R. So perpendicular to the R, I'll call it as V perpendicular, and that value of V perpendicular would be V sine theta. So that's your V sine theta. So that's your V perpendicular. So it is R V perpendicular. So if the whole velocity was perpendicular, it is actually sweeping the best angle possible in a given time. If it is slant, then it is not sweeping that much of angle. It is along R, it is not sweeping the angle at all. And what is R perpendicular? Now, even though it looks like considering V perpendicular is a convenient way, many a times you would rather be doing your R perpendicular. R perpendicular is this thing, the distance of the line of momentum, the line of velocity from the point of rotation, from the considered point of rotation, how far is the line of velocity? So it is somewhat like your force arm. If the force was like this to give a torque, so moment of force, we have done a bit of that early, so I can refer to that. So if your force was in this line and the force was like this, what would have been the force arm? This would have been the force arm. So that is your r perpendicular. Is it equal to r sine theta? This theta, this theta. So yes, it is equal to r sine theta. So instead of r sine theta, you can write r perpendicular. So that's the equation. So the best scenario is when the velocity is actually perpendicular to the radius. That's the radius, that's the velocity. That time it is simply m, this is the mass m, mvr, as simple as that. And what would be the direction? It's a vector. What would be the direction? R cross v, r cross v. So inside the board, in this case, inside the board. Now just to quiz you on this, just quickly tell me, in this situation, that's the mass, that's the considered point of rotation. It is going with v velocity forward. It is r1 distance away, and after a long while, it has gone over here. It is still going with v velocity forward, and it is r2 distance away, r2 being much greater than r1, in which case is the angular momentum more. So yeah, punch in your answer. In which case is the angular momentum more? This is your case 1, situation 1, that's the situation 2, when it has reached over there. In which case is the angular momentum more? This r1 was much less than r2, and it's going in this straight line. V is along the same straight line, and we are considering the angular momentum over here. So I hope you got the answer. The answer is, in both the cases, the angular momentum will be same, because angular momentum will be m v r perpendicular, and r perpendicular for both the cases, r perpendicular is this. So get a hold of r perpendicular. That is going to help you a lot. It is the perpendicular distance of the line of motion from the point of rotation. Anyways, let's come back to our agenda, that is demonstrating that whatever you are going to find in a rotational mechanics situation, you are going to land up with the term which is I. So let us do a calculation for angular momentum. So angular momentum would be angular momentum of each part added, and it's a vector quantity, mind you, but all of these will have an angular momentum which is inside the board, your r being from the point of rotation to the mass, that's your r, and the velocity is downwards. So r cross v is inside, so all of them will give you inside the board, and hence they can be a kind of scalar addition. It will be just algebraically added, all the ones which are all the angular momentum inside the board. So we will not worry about the vector part over here, and just the value. So the value will be mass. So we'll do the careful approach and not like finding the center of mass and getting the velocity of the center of mass, which will be again a job to do, but in a wrong direction altogether. So, and then doing a MVR of that is not going to land me with the right answer. What is going to land me with the right answer in this chapter is doing carefully finding the quantities for each and every part of the body, because each and every part is having various velocities. So this mass is m1, then comes your mvr. So what's the velocity of this? Velocity is, it's going downwards with how much velocity? Omega times x1 velocity, and r. What is the radius? What is the perpendicular distance of from the point of rotation? The perpendicular distance is x1 again. So that's your, so the velocity was in fact omega x1, but this distance is x1. Velocity of this one will be omega times x2, and the next one will be even larger. So angular momentum of the next one, mvr. So v is omega x2, r is x2. Next one, m3, omega x3, like this. You can keep on going, and what we see over here is omega is common for all, because it was, I shown to you earlier, it was a rigid body which is rotating, so sweeping same angles per unit time across, with respect to this point. So what we get is m1, x1 and x1. So if you had been wondering how the square is going to come, so it comes m1 x1 plus x1 whole square, m2 x2 square, m3 x3 square, dot everything and the omega outside. So we are going to get this term again. So this is the quantity which I am urging you, or what we are planning to pre-calculate for a given body, so that even if we had given it a big swirl and some other omega, the calculation of mass and its distribution about the axis in question remains same, and with a greater omega the L value would have been, the angular momentum value would have been greater. So this comes, and even when I go on to show you while you are calculating torque using your fundamentals of F is equal to ma very carefully, you still get your I term. So the point is, this I term is going to come again and again and again, and most of the bodies would be a continuous body. It will not be point bodies beaded into a massless scale. That is a quite an imaginary situation, just to explain you the scenario. And it would be continuous bodies, simple bodies like discs, like rings, like a rod, cylinder, stuff like that would be there, cuboids. Now let us deal with the continuous body and get the moment of inertia. I'm going to skip the part of getting the moment of inertia of bodies like these. Find the moment of inertia of this rigid body triangle. They are all together connected by light rods having given masses, and the distance from the axis in question is given to you. So it has been given to you, and you have to find the moment of inertia. I hope you can do m1 x1 square plus m2 x2 square plus m3 x3 square. So that is for discrete mass, and if I change the axis, then your distances will change and you'll get an altogether different answer. So we're not going to do this, but a continuous body thing. Now before we go on to finding the moment of inertia of various bodies, let me just talk a bit on the aptness of the term moment of inertia, what those words, why those words were chosen, and how it signifies the sluggishness or the laziness of the body in changing its state of rotation. So what M stood for in your translational motion, I will stand for a similar thing in your rotational motion. So M was in fact telling you, giving you an idea of the inertia of the body, how sluggish the body is while responding to external force on it, or how lazy it would be to change its state of motion. So I again is going to give you a similar idea. Like higher the I, the body will try to remain its state of rotation and won't start rotating with a higher angular velocity or a lower angular velocity unless a lot of external force, this time force with the distance from the point of rotation, so external torque, unless a lot of external torque is put on the body. So here, if it was a massive body, you required a big force to change its state. So otherwise the state will change very slowly, the response time will be slow. Here, if the I is big, then you will require a massive torque to make a fast change in state, otherwise the state will change very slowly. So it gives you like heavy flywheels. Flywheels have got big inertia, so they keep on rotating with the same velocity. So let me take this situation and say you had a force over here. It creates a torque. That force is having a force arm of this much, it creates a torque on the body, and this body starts rotating and has an alpha. So this torque and I and alpha is going to give you a relation on how much is the alpha, which is all the points will have various acceleration. So I can't say they are all having the same acceleration, but their alpha would be same, and R alpha will give the acceleration of each part. Now, keeping the force at the same point, say I say all the mass was right over here, was somewhere very nearby. Your force is still here, but all the masses were here. That's the thin rod, that's the massless rod. Then rotating it would have been much easier than had the mass all been there at that end. And you're putting the force again over here. If the mass is far away, all the masses are far away, then your effort taking in rotating would have been much more difficult. and similarly if the mass is distributed, it will be some other effort. So your inertia of this in the rotational motion will not only be given by mass but how it is distributed, whether the mass was near or far. If the mass is right over here and I want to rotate it, it would hardly take me any force to rotate it if the mass was right over there. If the mass is way away from the axis of rotation, it will take some effort. So you'll rather increase your torque by going towards there and then putting a force which is a greater torque. But I want you to compare same torque in all cases, same force and same force arm in all cases, and see where is the response time more. This mass way off will have a greater response time. So greater moment of inertia tells you, if it is far off, moment of inertia is more. So greater moment of inertia tells you how sluggish or how lazy the body is in responding to a external torque. So the inertia word tells you the sluggishness, and that sluggishness is coming not only because of the mass but also the distribution of the mass from the axis. Farther it is from the axis, more sluggish will it be. And the word moment gives the idea about this inertia is acting when the rotation is into play. So that moment term gives you idea of that we are talking about rotation of the body. It is going to mass as a moment about the point of rotation.